In this question, a scientist has a sodium hydroxide solution of known concentration and a sulfurous acid solution of unknown concentration. The scientist uses the sodium hydroxide as the titrant in the burette and a known volume of the sulfurous acid as the analyte in the conical flask. So to help us get a better idea of what's going on, in our conical flask, we have the sulfurous acid, which is H2SO3, and we're adding to that the sodium hydroxide, NaOH. Okay, so this question is a little bit more complicated because we have our strong base and we have our weak acid. But this time our acid has two hydrogen ions in it. We have H2SO3, which when fully dissociated would form two H plus ions and an SO3 2 minus ion. And the way that this actually works is that our H2SO3 first splits up into H plus and HSO3 minus, and then that HSO3 minus then splits up into H plus and SO3 2 minus. So we're actually going to end up having two stages in a reaction. First, we're removing one H plus from our H2SO3 to form HSO3 minus. Then we're removing the other H plus from that HSO3 minus to form SO3 2 minus. Again, the scientist measures the pH of the solution as the titrant is added. So again, we have pH on our y-axis and volume of titrant added on the x-axis. We can see our starting pH is 2, which is less than 7. That makes sense because we know that we have an acid in our conical flask, so it should be starting out with a pH less than 7. Firstly, we're asked what type of acid is sulfurous acid. Our options here are diprotic, monoprotic, and triprotic. So protic refers to protons, in other words, hydrogen ions. It's asking how many hydrogen ions do we have? If it's mono, then we have 1 H plus. If it's di, then we have 2 H plus. If it's tri, then we have 3 H plus. In this question, we have 2 H pluses. So this is going to be a diprotic acid. And if we look at our graph here, usually when we had our previous questions, which were monoprotic acids, we just had one of these inflection points or one equivalence point. In this question, since we have a diprotic acid, we have 2 equivalence points. So the first equivalence point here, that's going to be when this first reaction is complete, when all the H2SO3 has been converted into HSO3 minus. And then the second equivalence point here is going to happen when all the HSO3 minus has converted into SO3 2 minus. So let's again draw a diagram to help us visualize what's happening. So at the start, we have our H2SO3. Since that's a weak acid, only a tiny bit of it dissociates. So I'm going to show it all as our H2SO3 on our diagram. So that's at point A, we just have H2SO3. And a tiny amount of that will dissociate to form H plus and HSO3 minus because it's a weak acid. Next, we start adding some NaOH. So let's add some NaOH. That is a strong acid, so it's going to split up into its ions. And then what's going to happen here is that the OH minus is going to react with the H2SO3 to form H2O and HSO3 minus. So these are going to react, and we're going to get HSO3 minus forming and H2O, because one of the H pluses reacted with the OH minus that was added. We're not going to show H2O on our diagram though, just to make sure it's staying nice and simple and not too complicated. So at this point, we had 4 H2SO3 to start with. We added 2 NaOH, and that converted 2 of our H2SO3s into HSO3 minus. So at this point, we have equal amounts of our H2SO3 and our HSO3 minus, because we've added half as much NaOH as we started with. So that is going to be our half equivalence point here at B. That's going to be our first half equivalence point. We know that's a half equivalence point because at the first equivalence point, we have 0.04 litres added. So when we've added half of that, which would be 0.02 litres, that means half of our H2SO3 has converted into HSO3 minus. So we're going to have equal amounts of H2SO3 and HSO3 minus. So that's going to be here. We've got both H2SO3 and HSO3 minus. Now, when we get to point C, that is going to be our first equivalence point. At that first equivalence point, that's when all of our H2SO3 has reacted with NaOH to form HSO3 minus. So we're going to have to add 2 more NaOHs. Again, they'll be split up into their ions. And again, any OH added will react with H2SO3 to form H2O and HSO3 minus. But again, I'm not going to show the H2O on this diagram because I'm trying to keep it not overly complicated. So at this point now, we've got 1, 2, 3, 4 HSO3 minuses. We don't have any H2SO3 left because it's all been reacted with the NaOH that was added. So at this point, point C, the first equivalence point, we only have HSO3 minus. Now that is a weak acid, so that will be reacting with water to some extent to form SO3 minus. It's also a weak base because it's the conjugate base of H2SO3. So it's going to be reacting again with water dissociating to form back into H2SO3 and form OH minus ions. So there will be a little bit of our H2SO3 and SO3 minus in our solution at that point because this acts as both a weak acid and a weak base. However, it's a very small amount. Let's answer this question here while we're at it. We're looking at the first equivalence point here. That happens when the moles of NaOH added is equal to the initial moles of H2SO3. Because even though we have a 2-to-1 ratio in our chemical equation, we're just talking about the first equivalence point, which is where that first H plus from our H2SO3 has been reacted. So we just need 1 mole of NaOH to react with 1 mole of H2SO3 to form 1 mole of HSO3 minus. And that is point C on our diagram. Okay, so now we keep adding NaOH. So I'm going to add 2 more NaOH, again split up into its ions because it is a strong base. And now there's no H2SO3 left for the OH minus to react with, but it can react with the HSO3 minus. So now we're going to have this reaction happening. They're going to react together to form SO3 minus and H2O. Again, I'm not going to show the H2O on my diagram just to keep it simple. So there, again, we added half as much NaOH again as we had initially H2SO3. That reacted with half of the HSO3 that we had. So now we have 2 HSO3 minus ions and 2 SO3 2 minus ions. So we've got an equal amount of HSO3 minus and SO3 2 minus. So that's what's happening at point D. We can see there, point E is our next equivalence point. That's going to be where all of our HSO3 minus has reacted to form SO3 2 minus. D is halfway between C and D, between our first and second equivalence points. That means half of our HSO3 minus has been converted into SO3 2 minus. So at that point, we have HSO3 minus and SO3 2 minus. Then to get to point E, which is our second equivalence point, we're going to need to add enough NaOH that it reacts completely with all the HSO3 minus. So we've got 2 HSO3 minuses left. So I'm going to add 2 more sets of NaOH, Na plus and OH minus, Na plus and OH minus. Again, the OH minus is going to react with the HSO3 minus to form H2O and SO3 2 minus. Again, I'm not going to show the H2Os on my diagram. So at this point, point E, we now have 1, 2, 3, 4 SO3 2 minus ions. We don't have any HSO3 minus because it's all reacted to form SO3 2 minus. So now we have SO3 2 minus. Awesome. So we might keep adding NaOH now to get to point F. So let's add another couple of Na plus and OH minus. At this point, there isn't any acid left for the OH minus to react with. So the OH minus ions are just going to be in our solution, making it more basic. So we can see after E, we keep adding NaOH and our solution gets more and more basic. So that's what's happening at F. So in the end, we end up with still SO3 2 minus being the highest concentration of those ions. And we also have OH minus ions in there as well. Finally, we're asked, what is the pH at the final equivalence point? So here's our final equivalence point E, and our pH at that moment is 9. So it's greater than 7. Our pH is greater than 7. Why is the pH greater than 7 at this point? Well, at this point, all of our acid that we had initially has completely reacted. It's gone through both stages of having the H plus removed so that it forms the SO3 2 minus ions and H2O. However, SO3 2 minus is the conjugate base of a weak acid because that is then going to go on to react with water to form HSO3 minus and OH minus ions. So SO3 2 minus is a basic ion that's going to then go on to react with water to form OH minus, which is why we have a pH greater than 7 at the final equivalence point. So our answer here is going to be that SO3 2 minus is a weak base, so it reacts with water to form OH minus. So to summarize, in these questions, we have a weak polyprotic acid. Polyprotic means it has more than one H plus ion in it. And as it reacts with the base, it's going to remove one H plus ion first, and then we're going to remove the second H plus ion. So we're going to have 2 equivalence points for a diprotic acid or 3 equivalence points for a triprotic acid. So to figure out which species are present each moment, I recommend drawing a diagram to help you keep track of what we have. Remember our first equivalence point, that's going to be when the number of moles of base added is equal to the initial number of moles of acid. Our second equivalence point, that's going to happen when we've had twice as much added. So we've had 2 times the amount of the original acid added in base. If there's a third equivalence point, that's going to happen when the amount of base added is 3 times the initial amount of acid. Then we have our half equivalence points, which are halfway between each of those. And that tells us when half of our acid has been converted into its conjugate base. So that's why at points B and D, we have equal concentrations of an acid and its conjugate base.